All right, today we're putting on our detective hats. We're going to solve a mystery, but instead of a magnifying glass, we'll be using one of the most powerful tools in science, a really well-designed experiment.
So, let's get right to it. Here's our case. A teacher has a classroom goldfish, but for some reason, they just keep dying. It's a classic classroom conundrum, and the students are determined to figure out why. And you know what? So are we.
Now, when you're faced with a mystery like this, you can't just start guessing wildly. No, you need a plan, a solid procedure to make sure you don't miss any critical clues and that your final answer is built on actual evidence.
This step-by-step guide is pretty much the heart and soul of any scientific investigation. You've probably heard of it. It's the scientific method. Think of it as our playbook, the exact set of moves that's going to help us crack this case. It all kicks off with just looking around and ends with getting results you can actually trust.
Okay, so after watching what's going on, the class has zeroed in on a prime suspect. Their main theory, or what a scientist would call a hypothesis, is that the feeding schedule is the problem. It's a super clear, totally testable idea. Maybe, just maybe, the fish is being overfed.
So, with our hypothesis in hand, it is time to gather some hard evidence. Let's move into the investigation phase of this thing and see how we can build our case.
You know, in any experiment, there are a bunch of moving parts, right? Factors that could change and totally mess with our results. Scientists have a word for these: variables. Our job, as detectives, is to isolate the one variable we think is causing all the trouble.
Now, to test our idea the right way, we've got to understand two key players here. First, there's the independent variable. That's the cause. It's the one thing we are going to change on purpose. For us, that's how often the fish gets fed. Then we have the dependent variable. That's the effect. It's the thing we're going to measure. In this case, that's the health of the fish.
So, to make sure we're only testing the food and not something else by accident, we have to keep all those other variables exactly the same. We call these our constants, and they are absolutely crucial for a fair test.
I mean, just think about all the other things that could affect a fish's health. We have to lock them all down. So we'll use the same kind of goldfish, in the same size tank, with identical water, temperature, the same brand of food, even the same spot in the classroom. That way, we know for sure that any changes we see are because of our one variable and nothing else.
We also need a baseline, you know? Something to compare our results to. That's our control group. This is a fish that gets the normal treatment, fed every other day. We'll compare its health to our experimental group, which is the one getting the new daily feeding schedule. It's basically the experiment versus the status quo.
Okay, so as we start gathering our clues, our data, we need our measurements to be accurate. And that's a simple idea. It just means being as close as possible to the true, real value. But accuracy isn't the whole story. Our measurements also have to be precise. And this is all about consistency. If you measure the same thing over and over again, do you get the same result every single time? Think of it like this. It's a great analogy. Imagine you're throwing darts, and you hit the outer ring in the exact same spot every single time. Well, your throws are incredibly precise, but they aren't accurate because you were aiming for the bullseye, right? In science, we are always aiming for both.
So after 2 long weeks of careful observation, the results are in. Now we have to organize all this evidence in a way that actually tells a clear story. Let's take a look at a few different ways we can present our data.
Before we dive into our fish data, let's just do a quick review of our tools. First up, you've got your basic table. These are perfect for just jotting down the raw numbers as you get them, keeping everything super organized in neat rows and columns.
Another awesome tool is the bar graph. If you want to compare different groups, like, say, the top speeds of 2 different cars, it's a super fast visual way to see who comes out on top. Longer bar, bigger number, simple as that. And finally, we have circle graphs, which you probably know as pie charts. These are perfect for showing how different parts make up a whole, like the results from this very important, very scientific poll on hot dog toppings. It's all about seeing the proportions. Okay, back to our goldfish mystery. For our data, a line graph is going to be the best tool, since we're tracking a change over time. And it reveals the verdict. The control fish, the one fed every other day, was perfectly fine and healthy. But the experimental fish, the one fed daily, its health declined, and fast. We've got our smoking gun. So, with our evidence collected and laid out for everyone to see, it is time to officially close this case. We need to analyze what we found and deliver that final verdict.
And the conclusion couldn't be clearer. Our experiment totally supported our hypothesis. The teacher, who was just trying to be nice, was actually overfeeding the goldfish.
Mystery solved. And this just goes to show you, even if your gut feeling is right, it's the experiment that gives you the proof.
You know, our goldfish experiment was pretty straightforward because we could control everything and watch it all unfold. But what if you can't? What if you arrive at the scene of the crime late and all you have to work with are the clues that were left behind?
When that happens, detectives and scientists have to do something called infer. Inference is this amazing skill of using the facts and observations you do have to reach a logical conclusion about what must have happened when you weren't looking.
Here's a great example. No paleontologist has ever actually seen a T-Rex eat a meal, obviously. But by finding its fossilized droppings and seeing crushed up bones inside them, they can infer that its diet included smaller animals. They use the evidence that's left behind to reconstruct the story.
This whole process, observing, making a hypothesis, testing it, and drawing a conclusion, it's not just for chemists in a lab coat. It is a powerful toolkit for anyone who's curious about anything. It's really a way of thinking that can help you find answers to questions, big or small. So my question to you is, what mystery in your world are you going to investigate first?